Hello and welcome to Class 3, Physics 350, Electrodynamics. This is on integral vector calculus. It's chapter 1.3 of the textbook. And we're going to be working on integrals in three-dimensional space today, as opposed to the vector derivatives in three-dimensional space that we looked at last time. There are three types of integrals. There's the line integral, the surface integral, and the volume integral. And we're going to find next class that these types of integrals will connect with the vector derivatives, the grad, the div, and the curl through something called Green's theorem. Okay, so we'll find that out in the next class. So let's start with the line integral. The line integral involves integrating a vector field V along a curve C between two endpoints, B, A, and B. Okay, so if you imagine a curve between two endpoints A and B, we imagine integrating a vector field between those 2 points, A and B. And physical examples of the line integral include the work, which you're familiar with from Physics 201. That would be the integral from A to B of the force integrated with the displacement or the distance, and the voltage or the EMF, the electromotive force, which is the integral from A to B of the electric field dot, also with the distance. Okay, so these are examples of the line integral. So let's do a sample calculation. So we're going to calculate the line integral of the function v is equal to y squared x hat plus 3xy y hat. Okay, so this is just a function we're picking along the path from the point 1, 1, 0 in the plane to the point 2, 2, 0. And here's a picture of that in the plane. We have 2, 2, 0, 2, 2, 0, sorry, 1, 1, 0 is A, and 2, 2, 0 is B. And the Z component is not expressed here. So we can start out by noting that the component of the line integral is dl, small displacement. So that will be equal to a dx plus a dy plus a dz, all times the unit vectors. And along this particular path, we have that since x is equal to y, along this path from 1, 1 to 2, 2, we also know that dx is equal to dy, and also dz is equal to 0. And we need to use this type of information in order to eventually evaluate the line integrals in terms of integrals that we know how to do, as you'll see in a second. So let's start with the line integral. It's the integral from A to B of v dot dl, as we've already said. Plugging in v here, we have y squared x hat plus 3xy y hat, and I've put in a plus 0 times z hat here just for good measure, dotted with the differential dl, which is dx x hat plus dy y hat plus dz z hat. Okay, so let's see what we get. So that's just plugging in for the vector field v and the displacement dl. So looking at this, we see with x hat, we have x hat dot x hat is 1, we have y squared dx. And with y hat, we have 3xy times dy, okay, integral from A to B. But how do we evaluate this, the integral of y squared dx, okay, or the integral of 3xy dy? Because normally when we evaluate integrals, we have the integral of, say, x squared dx or of y dy. Well, here's where we use the fact that along this particular path, we know that x is equal to y, and that dx is equal to dy, because the path is a straight line with slope 1. So we can substitute for y, we can substitute x, and so we get x squared dx here. And the integral then runs from x equal 1 to x equal 2, point A to point B along the x direction. And we can substitute x for y, again, since x is equal to y, and dx for dy. And so we get the integral from x equal 1 to x equal 2 of x squared plus 3x squared dx, or 4x squared dx, which is something we know how to do. And we get the integral of, that evaluates to 4x cubed over 3, integrated from 1 to 2, which is, you know how to do this, plugging in 2 and 3, 32 thirds minus 4 thirds, or 28 thirds. Okay, so the key idea here is in evaluating the integral, the line integral, to actually, once we've substituted in for v and dl, to actually use the properties of the line, the direction, in this case, this straight line, to change these integrals into integrals that we know how to deal with, into one-dimensional integrals like we did here. Okay, let's move on to the surface integral. The surface integral involves integrating a vector field V over a surface S with varying orientation. Okay, so physical examples are the fluid flow rate. If we have a fluid flow V as a function of space, the surface integral of the fluid flow over an area will give us the total fluid flow rate out of that area, okay, because the velocity times the area is equal to the rate of fluid flow. And then the electric flux that you're familiar with, the integral over the surface of the electric field dotted with the dA that we talked about with Gauss's law a couple classes ago. Okay, sample calculation. This one gets a bit complicated, but let's go through it. So calculate the surface integral of the function v is 2xz x hat plus x y hat plus yz squared z hat over the unit cube. Okay, so here is a picture of the unit cube, and it's centered on the origin. And I've indicated the faces. 1, 2 is the back face, 3 is the right face, 4 is the left face, 5 the top face, and 6 is the bottom face. So we're going to have to do this integral for each of these faces. And I'll probably just do it for, say, 3 of them, and you can extend what I've done. Well, I'll do it for all of them, and you can, if you get the idea of how it works, you can forward in the video. Okay, so let's start off with the first face. For the first face, we know that x is equal to 1. Now, dA is the vector pointing away from the z-axis, away from the xy plane. So it's in the, away from the yz plane. So it's in the x hat direction. And the area will be dy times dx. dy times dx, since that's the two directions perpendicular to it. Okay? So then v dot dA will be 2xz dy dz. Why is that? Well, if we look at V, we have x hat, just an x hat component to dA. And if we look up here, we have just the x hat component of V is 2xz. So we have 2xz times dy dz. And since x is equal to 1 along the surface, we can simplify that to 2 times z dy dz. Okay, now we're ready to go. So the integral of v dot dA would be the integral from 0 to 1, since that's the integral of the unit cube of dy, times the integral from 0 to 1 of dz times 2z. The integral from 0 to 1 of dy is just 1. The integral from 0 to 1 of 2z, you recognize the antiderivative of that is z squared. So that just becomes z squared, which is 1 evaluated from 1 to 0, so 1 minus 0 or 1. Okay, so the surface integral out of this surface would be 1. Okay, let's move to surface 2, which is the back surface. Okay, a lot of similarities here, except that on the back surface, since this unit cube is centered at the origin, we have x equals 0, and dA, instead of being positive dy dx, dy dz x hat, points away from the outside of this surface. So it's going to be minus dy dz x hat. So then we have v dot dA is going to be minus 2xz dy dz. Before we had 2xz dy dz, now we have minus 2xz dy dz. But since x is equal to 0 on this back face, that gives us the integral of v dot dA is equal to 0. Okay, so there's no surface integral coming out the back side, side 2 here. All right, side 3 over here, we have here we have y is equal to 1 along this side, and dA then is going to point in the y hat direction, and it's going to have amplitude dx times dz. So v dot dA is going to be, if we look at the v here, the y hat component is x, and then we have dx dz. So we have x dx dz if we take this v times this dA, dotted with that dA. Okay, so we're able now to integrate over side 3. This says 3 here. It's a little bit light. I apologize. So we have v dot dA is going to be the integral from 0 to 1 of dx, since that's a unit cube, times the integral from 0 to 1 of dz times x. Well, the integral from 0 to 1 of dz is 1. The integral from 0 to 1 of x is x squared over 2, and so we get a value of evaluating to 1/2. Okay, I hope you're starting to get the hang of this. It's a little bit tricky, involving setting up the unit area, taking the dot product of that unit area with the vector field, and then using any properties of the surface that we're working with to simplify the expression that we get and make the integral doable. All right, moving on to side 4. Again, if you've gotten the gist of this, you can fast forward, but I want to reinforce this. Moving on to side 4, y equals 0. We have dA would be equal to minus dx dz y hat, the opposite of what we had on side 3. V dot dA will be the opposite of what we had on side 3, minus x times dx dz. So we have the integral of, at side 4 of v dot dA would be just minus the integral from 0 to 1, there's the negative sign here, dx times the integral from 0 to 1 dz times x. Okay, so it's just like this one, except with a negative sign because the unit vector is coming out to the left here. And so again, the integral from 0 to 1 dz is 1. And so we're left with the integral from 0 to 1 of x dx, which is minus 1/2. Okay. All right, we're almost there. Now let's look at the top surface, surface 5. There z is equal to 1, since we're on top of the unit cube. We have dA would be point in the z hat direction upwards, dx dy z hat, and we have v dot dA equal to yz squared dx dy. Okay, because we have the dx dy from here, and if we look at the z component of v, we have yz squared. So we have yz squared dx dy, which is equal to, since z is equal to 1, this z squared becomes 1. We have y dx dy. Now we can integrate over side 5 v dot dA. That would be the integral from 0 to 1 dx times the integral from 0 to 1 dy. Again, sorry, that's a little bit light. Times our integrand y. The integrand from 0 to 1 dx is just 1. The integrand from 0 to 1 y dy is y squared over 2, evaluated from 0 to 1, so that's 1/2. And then finally, we have the bottom surface where z equals 0. Again, dA is minus dx dz z hat, which is the opposite, dx dy z hat, which is the opposite of what we had before. So we have v dot dA would be minus yz squared dx dy, taking the dot product again of v, this part, with this part, which has dx dy, is equal to 0. And now with z equal to 0, this suddenly evaluates to 0. So we have minus y z squared dx dy is equal to 0. And we get evaluates to 0. So the total surface integral is then just going to be the sum of the surface integrals out of all of the individual sides. So it's going to be, the total will be the sum out of all of them, which would be 1 plus 0 plus 1/2 minus 1/2 plus 1/2 plus 0. So that's 1 plus 1/2 minus 1/2 plus 1/2, or 3/2. Okay, so that's in general how we do a surface integral over a shape with that doesn't have which is not a sphere, which doesn't have symmetry to it, or not the same degree of symmetry as a sphere has. Okay, finally, volume integrals. The surface integrals are probably the trickiest. The volume integral, we're integrating a scalar function t over a volume v, and physical examples of this include the mass. So if we know the density of an object as a function of x, y, and z, If we integrate that density with respect to x, y, and z, the density times the volume gives the mass, and so if we integrate that up, we get the total mass. And another application is the charge. So if we know the charge density, which could vary in space as a function of x, y, and z, we integrate that, we get dx, dy, dz times the charge density gives us the total charge. All right, so sample calculation. Let's calculate the volume integral of function xyz over this volume here, which I've called a pizza slice, okay, because it looks kind of like a pizza slice. It has x dimension 1, y dimension 1, and z dimension 2. So how do we do that? Well, we write the volume integral of t dx dy dz, and then we have to pick one axis to integrate over first. We normally pick the axis which is has an axis of symmetry, so the axis from along z, the shape on the xy plane is the same all along that z-axis. So we'd have the integral from 0 to 2 dz times what I've written here is the integral over this area, that is the area in the xy plane of xyz, of the quantity xyz that we're integrating over. So we'd have the integral from 0 to 2. Now this is the tricky part of the volume integral, which you may have run into in a math class or possibly not, but let's take a look at it here. As we move in x, okay, as we move in x, the limit of integration over y changes. So for x equals 0, our limit of integration would be 0 to 1. For x equal 1, our limit of integration would be 0 to 0. Okay, so the equation for this line is y is equal to 1 minus x. Okay, which you can check if you're able to check. So we want to integrate from 0 to 1 dx, but at each value of x, we want to integrate y from 0 to 1 minus x, because as I said, the integrand of the final integrand of y, the limit of integration of y changes as x changes. So this would be our expression, the integral of from 0 to 2 dz, integral from 0 to 1 dx, integral from 0 to y equal 1 minus x, dy xyz. Okay, this is something that now you would know how to do, although let's go ahead and do it. We have the integral from 0 to 2 of z dz times the integral from 0 to 1 of x dx, as we had before, times the integral to 1 minus x of y dy. So the integral of y dy is y squared over 2. So we plug in that limit of integration, and we get 1 minus x squared over 2. So this represents this integral here. Now we have the integral from 0 to 1 of x dx, 1 minus x squared over 2. And the integral from 0 to 2 of z dz is independent of that. That just becomes, it turns out that becomes 2, since this is z squared over 2, which is, plug in 2, which would be 4 squared over 2, which is 2. Anyway, you could figure this integral out. So we get 2 times the integral from 0 to 1 of 1 minus x squared x over 2, which you're perfectly capable of doing. I actually expanded that out, canceled the 2's, and you can multiply this out. I actually did it with Mathematica, and you come out with an answer of 1/12. So the integral of the volume integral of this function xyz within this pizza slice would be 1/12. All right, so that's line integrals, surface integrals, and volume integrals. And again, in future classes, we're going to be connecting those through something called Green's theorem to the divergence and the gradient and the curl. Thanks for your attention.